Good morning again, everyone on the West Coast. Good afternoon for those all the way stretching across the land from sea to shining sea. I am delighted to have you join us here for the Pitchfest at the 2022 National Energy Storage Summit. This is the most exciting part of the 2 days for me. My name is Danny Kennedy. I'm the CEO of New Energy Nexus. You can find me on LinkedIn at that QR code. I'm going to be the host for this exciting event, which we're going to run through pretty quick. We've got 15 finalists from many applications that came in for this Pitchfest. So you'll hear from all 15 representing multiple organizations around the country. And the presenters that you'll see have been challenged to give us their best ideas or solutions related to advancing energy storage in a variety of ways, but doing it in just 3 minutes or less using very limited visual aids. So these lightning talks is how you should think about them, could be about a new idea, an ongoing research project they've got, their startup company's mission, and whatever else they've come up with. You have a role in this too, our audience today. You will be voting and determining who wins 2 categories that we've coined the best presentation and the highest potential impact awards. So we're looking to you to pay attention to all 15 3-minute presentations so that then you can vote, and the ones with the most votes in their respective category will be crowned a Pitchfest champion from the National Energy Storage Summit. So this competition was already featured in Monday's edition of the New York Times, which just goes to show the importance of this summit and the 2,000 plus people we have coming to listen. Another example of how important the need for innovation and accelerating solutions for the United States, for the environment, the global economy. We've got to get this energy storage industry going just right. So we're going to introduce the Pitchfest presenters shortly, but before I do, just some criteria that we gave to the speakers so you can assess them with these in mind. We said that the presentation should be in language appropriate to a sophisticated but a non-specialist audience. That's you again. And the audience is going to judge them based on the relevance to the summit's themes that you've heard over the last day and a half. And the potential impacts, the question of impact is about how fast could this idea advance decarbonization in the US. Again, talks are limited to 3 minutes. The presenters are allowed to use up to 3 PowerPoint slides with animations if they have them. We'll be keeping tight time, and I'm going to jump back on stage. You'll see me come and interrupt if a presentation has gone over. While you're out there in the audience listening, if you do that thing where you have your phone in your hand and go on social media, you can contribute to the buzz that we're getting on Twitter using the hashtag Energy Storage Summit, hashtag Energy Storage Summit, all one word. Okay, here is the presentation order for today on screen. We're doing it in alphabetical order, as you can see, to keep it fair, but please do try to keep focused and pay attention to all of them to give them their due. They've put a lot of effort into this. And also I do want to thank all the other people that applied, and all of the presentations that we received will actually be posted and available online afterwards, as well as these 15 you're about to see. Okay, we ready? Without further ado, let's get started with our pitches. The first up is Alex Zorniger, the Vice President of Business Development at Power to Hydrogen. And his talk is Long Duration Energy Storage with Reversible Fuel Cells. Alex.
Thanks, Danny. Let me share my screen here. Okay. All right. Thank you for having us today. Let me get this out of the way. My name is Alex Zorniger. I'm the Vice President of Business Development at Power to Hydrogen, where we're doing long duration energy storage with reversible fuel cells. And we are a seed stage startup. So over here on the left, we have this graph showing the amount of, the duration of energy storage that we need in order to enable certain percentages of renewables powering our grid. Currently, America uses about 20 to 25% renewable energy. To get over 60%, what we really need is energy storage duration at least 6 hours or really 10 plus hours in order to enable those higher loads of renewable energy. Now, battery energy storage is great for short duration intraday energy storage, something shorter than 4 hours, where it's either solar shifting from peak times at day to later power usages at night, or peak shaving. However, it struggles with these long duration energy storage opportunities because it has a linear cost curve. When you need 1, 2, 4, 8 hours of energy storage, you just need to buy a consistently larger number of batteries. And so as long duration energy storages grow, the batteries struggle with this long duration need. So hydrogen creates an opportunity to solve this challenge. And the reason for that is because for hydrogen energy storage, you have an electrolyzer which produces energy. But once you produce the hydrogen, all you need to do is store that in a cheap metal tank or potentially an underground storage. So the longer duration of energy storage you need, hydrogen becomes more and more cost competitive. So you have on this graph on the left, kind of the difference between the cost curves for hydrogen and battery energy storage. Now, ARPA-E, the Advanced Research Project Agency for Energy, they say that in order for long duration energy storage to work, it really needs to be at the minimum 50% round trip efficiency to take advantage of the long duration cost efficient opportunity. So that's where our technology at Power to Hydrogen really comes into play and has a breakthrough opportunity. So conventional hydrogen energy storage systems need two different components. They need an electrolyzer to produce the hydrogen. These are typically 70 to 80% efficient, but they also need a fuel cell once they have the hydrogen to convert that hydrogen back into electricity. These are typically 50 to 60% efficient. That creates about a 35 to 45% round trip efficiency. At Power to Hydrogen, we've developed reversible fuel cells. So one unit can both produce hydrogen from renewable energy, and then also you can run that hydrogen back through the same unit to produce electricity. By doing it all in one unit, we're able to increase efficiency upwards to nearly 60%. And by doing it all in one unit, we're able to reduce capital expenditures by about 40% compared to a typical hydrogen energy storage system. And the technology so far has been validated by the DOE, Shell, and NASA. Thank you for the opportunity to speak today. If anyone has any interest in speaking with us and learning more, my email is in the lower right corner, and we're also in the networking area of the of the conference. So thank you.
Nice work, Alex. Thanks for showing us how it can be done in 3 minutes or less. Just Antonio, if you are able, as CEO at Inlyte Energy, I'd love to hear your lightning talk. Developing the proven Zebra battery for the grid. Antonio Baclig, CEO at Inlyte.
Yes, and it says I cannot share while the other participant is sharing.
That's no good. Andrew, do you think you can cut yours? Or maybe if Meg or anyone in the back office has an idea here about how we can unstick this. Okay, I am wondering if Justin, can we just cut Andrew so that he can work out his computer and get it out? All right, here we go. Thank you, Antonio.
Hi, my name is Antonio Baclig. I'm the CEO of Inlyte Energy. I only have your attention for 3 minutes, and I wondered, should I tell the story of our technology or the story of my journey? Then I thought, why not tell both? In the 1980s, the sodium metal halide or Zebra battery was born, invented by scientists in South Africa and the UK for electric vehicles. Also in the 1980s, I was born. In the 1990s, research and development on the Zebra battery proved it as a high energy density battery with very long cycle life and very good safety. Also in the 1990s, I was developing. In the 2000s, the Zebra battery made it into the world, commercialized by Mesdia, now FT Sonic in Europe, and also by General Electric in the United States. Also in the 2000s, I made it into the world with a mission to do something about climate and energy. But in the 2010s, things hit a snag. Lithium-ion batteries became the dominant battery for electric vehicles. And General Electric, for various corporate reasons, decided to cut the whole Zebra manufacturing plant, which led many scientists to jump to the conclusion that Zebra batteries just weren't good enough. I was one of them. I had come to Stanford to find an ultra low cost grid battery for the grid. And I spent 8 years researching novel ideas in hybrid flow batteries, but ultimately they ended up with too many challenges. So the Zebra battery was a proven battery looking for the right application. And I was a mission-driven scientist looking for a good battery for grid storage. Luckily, we met through online dating. Now, I've founded Inlyte Energy with the support of the Activate Fellowship at Berkeley Labs to bring this proven battery to the massively growing grid storage market. Let me tell you why I'm excited about it. Zebra batteries have a very low materials cost, which means that once the manufacturing is scaled up, they will have a lower cost than lithium ion. And they will not have the supply chain issues that we've talked about yesterday and today. They have a very long cycle life, which honestly is better for grid assets than for electric vehicles. They have an excellent safety record, which is important for certain locations such as urban areas. And there is room to optimize the Zebra batteries for the grid. Remember, they were designed for electric vehicles. And Inlyte Energy is working on turning those knobs with the Zebra battery to make them optimized for the grid and lower cost. I hope this story brought a smile or even a chuckle, but in all seriousness, I believe the time is now to bring the proven Zebra battery to the low cost storage the grid needs. Please get in touch. Thank you.
Thank you, Antonio. That was great. And remembering out there in the audience that we're going to vote at the end on best presentation as well as highest impact. So tell us the ones you enjoy when you vote. Next, we've got Bor-Rong Chen, a staff scientist at Idaho National Lab, and her talk is about the early detection of aging mechanisms in lithium-ion batteries, a machine learning framework. Thanks for being here.
Batteries are like human beings that age through time. During numerous charging and discharging cycles, battery aging can happen in many different ways. For example, lithium stops circulating, cathode materials are cracking apart, or overheating at local spots. Over time, a battery loses capacity and power, and eventually dead. We all want to make a battery live longer, and researchers are actually curious getting to know a battery's fate in advance. There are lots of research dedicated for battery lifetime prediction. These methods collect battery health data over time, then capture features and trends that can be projected to battery's remaining lifetime. While these methods can make accurate predictions, however, they are usually a little bit silent about what mechanisms are responsible for battery aging. And this is because that the features selected are usually mathematical based or data driven, which do not provide a lot of detailed insight behind it. Without knowing the cause of aging, we will have no clue about how to adjust battery operation conditions or to even redesign a whole battery to stop more aging from happening. And this is exactly where our research team at Idaho National Lab steps in. We are developing a method to identify who is the culprit behind degradation. And what we do differently is that we focus on using physically explainable features, the features that are the direct responses from different specific aging phenomena. So let's take lithium plating, for example. That is lithium deposited directly on the anode of the surface of the anode, which cuts down capacity dramatically and also causes serious safety issues for electric vehicles. So we would like to spot that on as early as possible. So here are 3 pieces of battery data that we care about: capacity fade, voltage, and kilometer efficiency. In this data, we discover trends such as linearity versus non-linearity, increasing or decreasing, that are physically bounded with lithium plating and respond coherently over time. These features were put together into a machine learning framework, and we formulate an aging decision tree. So whenever we feed new battery data into the decision tree, the tree will separate non-lithium plating cases versus lithium plating cases without even doing the effort of tearing down the cells before they are dying. With the same idea, we are working on building more of these decision trees that are targeting different aging phenomena. So going forward, these decision trees can be integrated into battery lifetime management systems to improve safety at lifetime, and also provide insights in design better batteries to resist aging in electric vehicle applications in the future. Thank you.
Fantastic. Thank you. Wow. A lot. Dense ideas about machine learning and batteries in 3 minutes. We've got it all going on here. Next up, we've got Brian McCarthy. He's a senior scientist at EC Power, and his talk is Goldilocks and enabling a true mass market battery pack using thermal modulation. This will be interesting. Goldilocks and the 3 bears or whatever. Go on, Brian.
Thank you, Danny. And I'm looking forward to sharing our take on this very classic story, which has a fascinating history if you look it up. So let's talk about chapter 1. Battery cells need to be just right. And by just right, I mean their temperature in an electric vehicle. When you're driving around, you don't want your battery pack to be too cold because then you have low power and low range. Rather, you want it to be warm, but not too hot because then you begin to degrade the cells. Now, if you want to fast charge those same batteries, you don't want them to be cold or warm because you risk lithium plating. Rather, you want them to be hot in order to have a safe fast charge. Finally, if your car is off, you really want those cells to be as cool as possible to limit self-discharge and calendar life loss. And this all points to the need for an active thermal management system. So, chapter 2. The status quo it consists of 2 general strategies. The first is air-only cooling. This is a very cheap method of cooling, and however is low performance. So this is utilized by the Nissan Leaf. And the low cooling ability means that it has really problems during highway driving and fast charging. Also, because you can't actually heat the pack using the system, it takes you much longer to fast charge. The more expensive and fancy option is liquid cooling / heating, as utilized by the Tesla Model 3, for example. Now, because you can actually heat your pack, you can fast charge in a much quicker time. Now, we believe the future is the thermally modulated battery by EC Power. Now, I'm going to explain what's inside our cells because this is all patent protected. I'm allowed to tell you this. Notice we have a third terminal here called heat. Let's take a look inside. We have our standard cathodes and anodes. We also add, however, a very thin resistive heating element. And we think about a simple circuit diagram here. When this switch is open, nothing is happening. But if you close that switch and connect your cells to an external charger, you run heat through the circuit and generate heat very quickly, uniformly from the inside out. And then you can safely fast charge. Now, the major advantage here is that you take the status quo liquid cooling time from 30 minutes and you drop it to 30 seconds. And we believe this is really going to enable a true economy car using our system for on-demand heating, designing higher temperature cells, which can then effectively use air cooling, using our on-demand heating in order to enable cheaper materials, as well as energy-dense solid-state and lithium metal cells, both of which require higher temperatures for good performance. Now, you don't have to believe me. Our technology has already been utilized in the public buses of the Winter Olympics, licensed by BMW, and third-party verified by Argonne National Lab. And with that, I thank you, and I'm looking forward to a future where the just right temperature is available on demand.
Goldilocks, you did it. Well done. Just right in time as well. Thank you very much for that, Brian. Now we're going to go to Danny, not me, but to another Danny, Ushizima, and she is an applied Mathematics and Computational Research Division staff scientist at LBNL, at Lawrence Berkeley National Lab. Her talk is Advancing Lithium Metal Battery Design with Deep Learning. Danny.
Thanks, Danny. Here we go. Have you ever wished batteries to be lighter and with a higher energy density? What if a new battery design leads to fire and explosion? I'm Danny Ushizima, and I help material scientists to detect battery defects by transforming X-ray images into information. Why? Because defects such as dendrites can occur both in the standard batteries, namely lithium metal batteries, as well as the more advanced lithium metal batteries. Lithium metal batteries, or L and B, use the solid electrodes and electrolytes to provide superior electrochemical performance. This means increased charge storage capacity and the ability to hold almost twice the energy of a traditional lithium ion. Before manufacturing a new L and B design, one battery test consists in quantifying the deposition of lithium during battery charge. If the deposits form spiky clusters, we have dendrites. And if they grow, as I illustrate with our data at the bottom of this slide, that can lead to an explosion. So which are the factors that control the formation of these defects? Understanding how dendrites form and grow is key for safer designs and preventing any short circuit. That's why we use the tomography data to look inside batteries during charge and discharge cycles. But looking is not enough. Taking pictures is just the start. Quality control and quality assessment requires quantifiable metrics. This means detecting and measuring dendrites automatically. That's what we do. We create deep learning algorithms to automate inspection of battery data acquired with advanced instruments at DOE national laboratories, such as Oregon National Lab APS facility and Berkeley Lab ALS facility. By using X-ray tomography as input data, as well as prototypes defined by our battery experts, we detect battery defects and measure their growth during battery cycling. Together, our team has created a new set of machine vision machine learning algorithms based on convolution neural networks focused on three-dimensional X-ray data evolving in time. Only by identifying L and B defects and tracking them during cycling, we can monitor the lifespan of a battery and the evolution of the dendrites. If you need help understanding the hidden patterns within your battery and accelerate energy innovation, we are ready. Contact us. I'm Daniel Shizima, member of CAMRA, and I lead the machine vision research team behind this investigation. Thanks for listening.
Thank you, Danny. That was wonderful and right on time as well. I really appreciate everyone's discipline with this. I hope the audience is enjoying the pictures and remembering they're going to get to vote in just a bit. David Mechanic is next. He's the CEO at Anthro Energy. And the presentation is going to be robust polymer electrolytes enabling flexible and structural batteries. Go, David.
All right. Hi, everyone. My name is David Mechanic. I'm the founder of Anthro Energy, where we're changing the shape of energy storage. Anthro Energy is developing advanced polymer materials to enable new forms of energy storage. Today's batteries use polymers to hold together every single part of the battery, but these polymers are some of the oldest known polymers, and they're several decades to a century old. These materials are typically linear, and they're not that smart, and so they're kind of monofunctional and not highly tunable. At Anthro Energy, we're introducing advances in polymer chemistry that have been developed over the last 20 years to enable tunable materials that are smart. They can be tailored to any application they need. They are multifunctional, and they can impart a huge range of material properties into battery cells for new forms of energy storage. There's a huge range of applications with this platform polymer material technology that we developed at Stanford University in the research group of Professor Chen Bao. They can be used for flexible batteries, structural batteries, and to enable next generation chemistries such as silicon anodes and lithium metal anodes. At Anthro Energy, we're starting by commercializing flexible batteries because of the clear differentiation and high applicability across a wide range of industries. The flexible batteries enabled by Anthro Energy polymer technologies are flexible, meaning you can bend and deform them like the cell that I have in my hand here. They're versatile, meaning you can put them in places you haven't gone before, such as dead space of devices. And they're also highly safe. Our batteries can be cut, punctured, and even exposed to flames without catching on fire or causing any safety issues. By using these batteries as either the straps, substrates, or bands in devices, we can create 2 to 5-fold improvements in device life across a wide range of applications, including IoT devices, advanced wearables, flexible electronics, and medical devices. In the future, we envision this flexible and safe energy storage to even be used for larger scale structural applications to create safe power in places that you couldn't put it previously in things like drones, EVs, and even more. Today, our initial markets are already quite big and quite important to society. It's projected by 2025, there will be 75 million IoT batteries produced every single day, which represents a market size of over $5 billion. The high performance and rechargeability of Anther Energy's batteries could result in longer lasting devices, reducing electronic waste. Additionally, there are over 600 million wearables sold every year that provide invaluable information about human health, and our batteries could dramatically improve their performance. Already, our technology is ready for testing, and we're engaged with early customers via our demo kit that we've developed at Anther Energy to demonstrate our highly performance, high flexible battery technology. Anther Energy is formed in an alliance between Stanford and Berkeley with me and my friend Joe, and we're supported by a number of great programs, including the Activate Fellowship, National Security Innovation Capital, and others. Thank you.
Ding, 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 ding. Done. Well done. Thank you very much for a fascinating presentation. And now moving right along to another. I hope you're all keeping up out there in the audience. We've got Dula Parkinson. He's Deputy for Photon Science Operations at the Advanced Light Source at Lawrence Berkeley National Lab up on the hill there. And his talk is X-ray vision into energy storage. Dula.
Hey, thanks. So yeah, I'm Dula Parkinson. I'm a scientist at the Advanced Light Source at Berkeley Lab. And I've got a question for you. Have you ever wished that you could have X-ray vision? So I've got good news for you. Today you can. So how do you like it? Is it nice? So normal X-ray vision like this is fine and all, but what if you want to look inside of a battery in microscopic detail? For that, you're going to need a more advanced form of X-ray vision. So I've got good news. The Advanced Light Source, or ALS, is a place that can give you that kind of advanced X-ray vision. The ALS is a specialized particle accelerator that generates very bright beams of X-rays. This is a diagram that shows the 40 or so different beam lines where X-ray beams are used to do experiments. The magical thing about working at the ALS is not just that there's beam lines, it's that the ALS is a user facility. Berkeley Lab is all about team science, but a user facility at Berkeley Lab takes team science to another level, because in addition to the staff that we also have thousands of users who come and bring their unique ideas and perspectives to the ALS. Today, I'm going to tell you about a few of the experiments that users have done with ALS beamlines. First, Natash Balsara. He's worked with me at the micro CT beamline to image lithium batteries. During charging, what you'd like is for lithium to go evenly into the graphite anode at the bottom here. But what they saw during fast charging is that some of the lithium gets stuck as lithium metal and blocks lithium ions from going in evenly. Of course, the images help us understand why this is happening and how to prevent it. Another example, Will Chu and his collaborators from the National Center for Electron Microscopy have worked with David Shapiro with the Cosmic Beamline to be able to compare 4D STEM data with spectrotachography data. This allows them at nanometer scale to compare the composition to the structural strain. And by knowing this relationship, they can then look for defects and see how those affect things in battery cathode materials. Unfortunately, I don't have time to tell you about all the different things we're doing at the ALS. Let me just mention a few more. Brett Helms has worked at the STAX beamline to look at selective membranes. Wanli Yang has worked with users at the RIX beamline to look at redox states in oxygen and metals. Ethan Crumlin has worked with users at the ambient pressure XPS beamline to look at how carbon dioxide affects lithium metal surfaces. Let's just say there's a ton of different things you can do with X-ray vision at the ALS. Okay, so now what if you want to come to the ALS? You should check out our website, als.lbl.gov, and learn more about us. Then reach out to a staff member. I would love to show you around sometime. Together, we can solve the greatest energy challenges. I look forward to seeing you at the beamline. Thanks.
Thank you. That was awesome, Dula. I felt like I was there and going down the rabbit hole with your interesting PowerPoint slide setting, and great to hear about the team sport up on the hill and how we can come and play. So I hope you're all geeking out there in the audience and getting into this. The next one's going to keep it rolling. Jan Naidu is the CEO and founder of Revolt Battery Technology, and his talk is the reactivation of cathode materials from spent commercial lithium-ion batteries.
Hello, my name is Jan Naidu, and I am co-founder and CEO of Revolt Battery. The first wave of retired lithium-ion batteries is expected by early electric vehicle adopters by 2023, with over 45,000 battery packs containing tens of millions of lithium-ion cells coming out of service. As a consequence, global demand for critical materials used in batteries such as lithium and cobalt are expected to grow at similar rates, leading to increased supply chain risks. To be specific, the global demands for lithium and cobalt alone are expected to increase around 10-fold from 2020 to 2030, surpassing the current supply. Cobalt is produced mainly as a byproduct of nickel and copper mining, primarily from the Congo. Revolt is an environmental and socially responsible Houston-based startup based out of the University of Houston's Innovation Center, set to transform the world's energy challenges into the world's biggest business opportunities. When batteries are retired from automotive service, they still have from 50 to 70% of their initial capacity. This opens the possibility to repurpose them for energy storage applications until they are eventually recycled. The reuse of end-of-life EV batteries as energy storage systems after automotive use is an opportunity to improve the sustainability of batteries. Revolt is building an ecosystem, including a software platform to support stationary applications and direct recycling of automotive batteries with different electrochemistries. Our mission is to enhance energy storage by enabling secondary use of end-of-life batteries. Our vision is to enable a circular economy approach for EV batteries in the United States. We are actively seeking academic research, commercial, and defense partners. So do reach out to us, and thank you for the opportunity.
Thank you, Jan. That was wonderful to have you dialing in from Texas and telling us about the opportunity for the full circularity of this incredibly important industry we've been discussing at the National Energy Storage Summit. We're in the middle of our Pitchfest, just for those of you that are dialing in, and we're getting through 15 fantastic explanations of opportunities in that space. Jason Cottrell is next. He's the founder and CEO at Arcam Technologies. And his talk is 3D concrete printed subsea pumped hydro electric storage, getting out of the batteries and into the sea. Go on, Jason.
Hi, I'm Jason Cottrell, founder and CEO of Arcam Technologies, a growing startup with offices in California, Colorado, and Scotland. I started Arcam 5 years ago after a 20-year career at NREL, where I learned about an emerging technology called 3D concrete printing that cuts the cost of concrete construction in half. And my PowerPoint crashed. Can you still hear me?
We can hear you, but yeah, your PowerPoint has disappeared. So
Microsoft.
if like, we could possibly move on, and I can come back to you after we come back to Anna.
Sounds good. Okay, thank you.
Thank you. No worries. Thanks for being flexible here, folk. Just keep it in mind out in the audience, and I'm going to call on Catherine Ott, if I can. She is a research associate at PNNL, Pacific Northwest National Lab, and the Decision Modeling and Optimization Group is her team. It's talking with Team Science. Her talk is VRE Complement Optimization. Catherine.
Thank you. Hi, everyone. My name is Catherine Ott, and I'm a research associate at Pacific Northwest National Laboratory. Both individual states and the federal government have set ambitious goals to decrease greenhouse gas emissions over the next 30 years. However, these goals are only possible and economically sensible if the grid is flexible enough to incorporate large percentages of variable renewable energy like wind and solar. Currently, the grid cannot easily handle large, quick shifts in power generation. Above 30% VRE, there is limited alignment between power supply and the demand for electricity. So these sources of renewable energy offset less and less fossil fuels generation, which decreases their decarbonization potential and their economic value. Beyond fast responding generation, like natural gas turbines, options to balance supply with electricity demand include storage, which shifts supply, and demand response, which shifts demand. However, the point at which storage and demand response are economically viable is hard to identify due to variability by region, availability, and unassessed costs. That's why I propose VRE complement optimization, a multi-objective optimization tool to decide when power smoothing options are viable and useful to the grid, and if so, which storage technologies and types of demand response programs to incorporate with VRE generation. Each option has economic considerations, benefits, and challenges to both the power grid and to neighboring communities. The ease of incorporating these power smoothing options and the extent of potential outcomes depend on many factors. This project would parameterize the factors shown here and create a web-accessible tool. It's different because it includes cost as a factor rather than solely being a cost minimization problem. Various stakeholders, like communities, utility companies, and policymakers, could use this tool to change the weights on each factor in the optimization equations, and then they could have data-informed discussions based on their varying priorities about what the optimal solution is for their specific situations. Now, I want to focus on one of the bottom factors, additional equity benefits. Energy storage, particularly if it enables the decommissioning of emissions-producing power plants, can provide a wide range of benefits to local communities, from avoiding outages that put vulnerable groups and critical services at risk to enabling land to be repurposed for community or commercial uses. Historically, energy storage has been hard to justify due to difficulties associated with assigning value to these potentials. That's why a large part of this project would include determining a way to quantify these tangential benefits. This project would survey impacted communities and review existing data to formulate parameters describing the costs and benefits of energy storage to nearby communities, therefore creating a more holistic view of the impacts and opportunities of energy storage. Thank you for your time.
Thank you for your time and for drawing our attention to the incredible importance and an opportunity to have positive equity impacts from this energy storage uptake we're talking about. Justice 40 is talk of the town in Washington, D.C., and could be a big part of this going forward. We're going to move on to our last four and then come back to the two that had technical difficulties. So thanks again, Catherine. Next up is Manas Patek. He's co-founder and CEO at EarthN. His talk is Energy Pod for longer duration energy storage.
Thank you. Hope you see my slides.
Yep.
All right. Good afternoon, everyone. My name is Manas Patek, PhD chemical engineering, founder of EarthN. We are trying to solve, we have expertise of almost 50 years cumulative from our advisors to co-founders in the energy ecosystem, trying to solve the famous problem, solar and wind are intermittent sources of energy. And how could we solve it? Well, if you could store the VRE surplus in some sort of energy storage, which is the theme of this conference, you could solve this problem. And you have three types of energy storage: short, long, and seasonal. We at EarthN focuses on longer duration of energy storage, which is 6 hours plus, by introducing our patent pending product called Energy Pod. What is Energy Pod? You see on the bottom right is the schema of Energy Pod. It's basically a modular patent pending system made up of two modules: ECP, which is the energy conversion plant, whose job is to convert stored energy back to electricity and give it back to the grid. The storage itself happens in form of supercritical CO2 sitting inside this HPS system, heated pressurized storage, which could be under the ground for gigawatt capacity or on the ground for megawatt capacity, just how you see our energy pod sitting next to a windmill. Now, we are highly scalable, no geographical or geological constraint to the deployment of Energy Pod, looking at a target levelized cost of storage of $40 per megawatt hour and 60% of round trip efficiency. We hope to serve our customers, which are utility providers, solar and wind farm developers, and enterprise customers, as storage energy storage as a service business model to capture the $8.5 billion worth US dollar market, which is our beachhead market by 2026. And to do that, we are raising 100K right now to demonstrate the technology. So if you're still wondering, how does it work? Let's look into where do we fall in terms of the competing tech. We fall in this blue box, providing discharge time of 6 hour plus, 10 hour plus, and a storage size of 1 megawatt to gigawatt range. And how it works is, if you have excess energy at 12 p.m. noon in the state of California, you give it to Earth, we pump supercritical CO2 in the heated pressurized system, much like how you inflate a balloon. Let the stored energy sit inside this HPS systems, and when you want it back, such as 11 p.m. at night, we release CO2 through our energy conversion plant, which has the patent pending IP to convert with the best and great efficiency the stored energy back to electricity, much like how you deflate a balloon. So with that, I hope you join our mission. Our immediate success metric is demonstrating this technology once again at 100K raise to demonstrate with the metric of LCOS $40 per megawatt hour and round trip efficiency of 60%. Thank you.
I like it. Thank you, Manas. That was a very direct pitch for this Pitchfest. So good on you. And next, we're going to go to Nan Liu. Nyan is an assistant professor at the School of Chemical and Biomolecular Engineering at Georgia Tech. Lovely to have you in the house, Georgia. His talk is coaxial microtubular, CAMT to the pros, that's what we call it, coaxial microtubular flow battery with ultra-high volumetric power and continuous manufacturability. Over to you.
Thanks, Danny. My name is Nian, and I work at Georgia Tech. And our team has invented a way to increase the volumetric power density of flow batteries. So flow battery is a promising technology for storing energy in the large scale. And it has two components. One is the tank that stores the electrolyte liquid. And the second is the cell, which is the most expensive part in the battery system. And our innovation is on the cell. Conventional cell use a planar configuration as shown here. And our innovation is a microtubular configuration. And if we look at each one of these tubes, it has a Nafion membrane, tubular membrane here with an electrode inside and another electrode outside. And the electrolyte, one of them flows inside the tube and another flow outside of the tube. And this kind of configuration from finite element analysis can give you a much higher current density at the same cell voltage. And we assemble the cell, and the cross-section image look like this, and it's very small. And we have demonstrated this using the vanadium redox chemistry. And this is how our lab scale demonstration look like. So the reason for this boost of volumetric power density is coming from the small size of the membrane. And so you can place the membrane in a distance that's 100 times smaller than the conventional one. So this gives you theoretically 20 to 30 times increase in the volumetric current density or the volumetric power density. And this can save you a lot of footprint and also cost in making the cell of the flow battery. And we have demonstrated here in this plot that compared to the existing technologies, ours is around 10 times higher in terms of the volumetric power density. So we are currently using the Nafion microtubes from a commercial source, and we think this technology is very scalable. You can make bundles of these microtubes together, and we have done this in the chemical separation. And in fact, the water desalination also choose these kind of tubular configuration rather than a planar one. So we think this applying this to electrochemical flow battery is a very promising and feasible way.
Excellent.
Thanks.
Thank you, Neon. And there's the contact too for collaboration, which we'll come back to after all the pitches, but that was wonderful. Thank you. Going to move right on along to Ryan Klabundi. He's CEO at Cryostone, and his talk is about a thermochemical approach to energy storage.
Hi, can you see my screen?
Yes, we can.
Okay, perfect. Hi, I'm Ryan Klabundi. I'm co-founder and CEO of Cryostone, and I'm here to talk to you today about a thermochemical approach to energy storage using liquid compressed air energy storage. So, this slide has a lot of figures on it, numbers, but these are numbers from Department of Energy's Energy Storage Grand Challenge final report. And what it shows is that compressed air energy storage is cost advantaged versus all other technologies at all durations, including lithium ion, not only today, but in 2030. So that begs the question, why are there only 2 commercial utility scale operations globally for compressed air energy storage? We at Cryostone believe it's for 2 reasons. One is siting constraints, which means geology. And second is that the thermal efficiencies proclaimed for compressed air energy storage vastly exceed the reality that is experienced. So that got us wondering, what if we could remove these 2 constraints? Well, it would really open up the ability to pair storage with solar in any location for any duration at much cheaper costs than batteries and at longer life, even in high cycling environments. Cryostone's technology, which has patents pending, solves these 2 problems using a combination of temperature swing adsorption and direct heat exchange to create liquid compressed air. We've proven this at lab scale. It's confirmed the models. Our thermal efficiency is on the order of 85 to 90%, which would translate into round trip efficiency of no less than 60%. Our system has no capacity fade in higher cycling environments. And given that the materials of construction are steel tanks and rocks, the supply chain is more sustainable and it provides a more intrinsically safe operation. We're currently TRL level 3, that stands for technology readiness level, and we're looking for partners, both industry and government, to help us take this technology from TRL 3 to TRL 6. I want to thank you for your time. If you have questions or have follow-up, you have our emails here of the co-founders, Nikki at cryostone.com, Ryan at cryostone.com, or you can visit us at www.cryostone.com. Thank you.
Cool, and thank you, Cryostone. It's great to learn about that potential for LCAES. Now we're going to move on to underground pump storage hydroelectric, which is another fascinating topic. It's going to be presented by William Taggart, a consulting engineer at Taggart Engineering.
Welcome. With the focus on batteries, thermal storage, and hydrogen, I want to shift and discuss pump storage hydroelectric. Conventional pump storage is the backbone of America's existing energy storage with the most capacity and almost 98% of the electricity storage, but is limited to areas where the geography supports it. You need to be able to build large water storage reservoirs with enough height between them to make it worthwhile. As such, it prevents this technology from being used in areas that are relatively flat. Underground pump storage hydroelectric is one of the ideas that has been discussed, and this is what we are working on, a new approach using salt dome caverns. If you're not familiar with salt domes, they are massive underground structures of salt, plain normal salt. Companies have been solution mining the salt and creating storage caverns since the 1960s. Those caverns are then used to store oil, natural gas, and other fluids. The Department of Energy has 4 locations where they store oil as part of the Strategic Petroleum Reserve in salt dome caverns. Salt domes exist in Texas, Louisiana, and Mississippi. The area covered by salt domes is home to more than 25 million Americans, an area that DOE estimates needs over 75 gigawatts of energy storage. but is too flat to use conventional pumped storage. Underground pumped storage hydroelectric will use salt dome caverns for the upper and lower reservoirs of a closed loop system. Compressed air would be pumped into the caverns to turn them into hydroelectric reservoirs. The compressed air raises the surface pressure of the fluid piping so that the hydroelectric turbine acts just like a conventional pumped storage. When excess electricity is available, brine is pumped from the lower reservoir to the upper reservoir, with the compressed air freely flowing in the opposite direction. When that electricity is needed, brine flows from the upper reservoir to the lower through a hydroelectric turbine, making electricity. The technology would be close to 80% efficient and would be just as reliable and dependable as existing pump storage installations. The system can store 26.4 megawatt hours of energy per acre of salt dome. It would complement large wind farms and solar farms along the Gulf Coast and could even be built in tandem with them, as the bulk of the installation is underground. Only the wellhead pipings and powerhouses are on the surface. The rest of the land is available for other uses. We are presently developing this technology and are looking for investors to build a demonstration unit. The initial demonstration unit is less than 1 megawatt and we use 2 existing salt dome caverns. A second demonstration unit is planned, which will have a 5 megawatt turbine and store 50 megawatt hours of electricity using 2 salt dome caverns built for optimum energy storage. We hope you will join us on this journey, and thank you for listening.
Well, thank you, William, for explaining that fascinating use of the salt domes. I knew about them for the Strategic Petroleum Reserve, but hadn't thunk of that. So wonderful to hear it in the Pitchfest. We're now going to go back to the couple of folk that had technical troubles. I think Andrew Tanner will go first. I think he's blaming Zoom, but it's good to have you back. VP of Growth and Strategy at Yotta Energy, talking to us about panel level energy storage, storing energy at the source. Andrew.
Great, thank you, Danny. My name is Andrew Tanner. I'm VP of Strategy and Growth at Yotta Energy, and I'm here today to tell you about the world's truly first integrated solar plus storage technology. At Yotta, we pioneered an entirely new PV-coupled architecture for integrating energy storage with solar on buildings. As you can see in the picture shown, our technology installs beneath solar modules and stores energy directly at the source.
Andrew, I am going to interrupt you just so you don't get surprised when you hear this afterwards. Your screen is still not sharing, to me at least. I don't know if it is for anyone else, but I imagine it. I'm seeing your words become pictures, and I think you should just persist.
You know what? I have a backup plan. So let me see if
timekeeper, may we please give Mr. Tanner a 30-second break here?
Okay.
If not, we're going to post all these on the website afterwards, so you can submit a video there, Andrew.
Can
have trouble with the Zoom, I guess.
So just give me 1 second, please.
How about I go to
okay.
Nope.
Let's do that.
Go to Jason. Great. Jason, I hope you're ready again. I think it was Microsoft you were swearing at as we last saw you, but thanks for coming back. Founder and CEO at Arcam Technologies, talking about 3D concrete printed subsea pumped hydroelectric storage, a good follow-up to the salt caverns.
It could be Microsoft, Mac, or Zoom. I don't know who to blame. Let's
not be blaming brands right now. I guess we shouldn't.
Let's try this one more time.
Great. Hey, you're looking good. Go ahead.
All right, great. So, hi, I'm Jason Cottrell, founder and CEO of Arcam Technologies, a growing startup with offices in California, Colorado, and Scotland. I started Arcam 5 years ago after a 20-year career at NREL, where I learned about an emerging technology called 3D concrete printing that cuts the cost of concrete construction in half and speeds production. The automated manufacturing technology uses 3D printing methods with low-cost concrete materials to eliminate concrete formwork and enable new designs while maximizing local manufacturing. Arcam is dedicated to using this promising new technology to manufacture the long-duration energy storage we need to reach net zero. A lot has changed since leaving NREL 5 years ago, especially in offshore wind. In land-constrained, highly populated coastal areas, offshore wind is the only way to reach decarbonization. As a result, US offshore wind is growing exponentially in the US with a 700 times increase expected over the next 8 years. The US already has about 40 offshore wind lease areas, creating a pipeline of new wind deployments that will power 10 million homes by 2030. But how are we going to cool and heat our homes when the wind stops blowing and solar isn't available? Batteries are too expensive still for long durations, and other technologies too inefficient or far from commercialization. We need a new low-cost energy storage technology to solve this grand challenge. The subsea energy storage technology we are developing can solve this challenge. Our marine pumped hydro storage system can provide all the low-cost energy storage needed to keep power flowing to our homes and businesses when offshore wind turbines stop. The working principle is straightforward. It's a form of modular pumped hydropower. We 3D print lightly reinforced concrete spheres in ports, float them to wind plants nearby, and lower them to the seafloor. Inside each sphere is a reversible pump turbine assembly. To charge the system, you pump out the low pressure water through a pipe to the high pressure water outside the sphere. The process is reversed to get the power back through a turbine. The concept has been proven, is 80% efficient, and is the lowest cost offshore electrical storage available. In addition, we will 3D print them locally in America's ports, creating good paying jobs. We've won the grant funding needed to build and deploy a small scale prototype and are seeking VC funding to scale up. So all we need now is a little support from you to help raise awareness about this idea. So please contact us if you're interested in developing this technology with us, and vote for our pitch to help raise awareness of this technology. Thank you.
Thank you, Jason. And one last chance, Andrew. Let's just quickly go back. Yotta, you got it? If not, we're going to have to move along.
No worries. So Danny, I'm not going to actually show slides. I'm just going to provide my camera because I can actually put the slides behind it. So hopefully everybody can see my
Go ahead. Yep.
See me now. My name is Andrew Tanner. I'm VP of Strategy and Growth at Yotta Energy. I'm here to tell you about the world's first truly integrated solar plus storage energy storage technology. As you can see on the rooftop here, our battery installs beneath the solar module directly at its source of generation. Now, what enables this technology is a phase change heat exchange thermal management approach, which is entirely passive. And there's three key components to this: a layer of ceramic material that provides insulation and also doubles as fire protection. We have a mass of phase change material which absorbs energy once the temperature internally gets to 100 degrees Fahrenheit. And then thirdly, we have a heat exchanger that rejects energy to the environment overnight, regenerating the phase change material and allowing the product to cool down to 70 degrees Fahrenheit. We validated this technology at multiple different labs, and we're in the process of UL certifying and we'll be shipping commercially available product in Q3 this year. Now, one of the advantages of this approach is the architecture. Traditional solar installations have a DC ratio of 1.3 or thereabouts, which has a small amount of clipping, but it actually underutilizes the solar inverter, and it only operates about 1,000 hours at full output. What Yotta can in fact do is enable that DC ratio to increase to 2, thereby utilizing the inverter for longer, operating at its highest efficient point, which is maximum output, but in fact reducing the number of hours that the inverter is actually running at. This has other benefits. We're minimizing the amount of AC sizing of the system by about 40%. That reduces the cost of the solar installation by about 20 cents a watt, which, to put that into context, is about half the price of a solar module. So there's material impacts that this architecture is having to reduce the cost of the solar installation itself. So in summary, this approach is truly the world's first solar plus storage system where the technology is integrated at the source of generation. We dramatically simplified the design and installation with a zero maintenance approach. It's entirely solid state. We provide maximum flexibility at the highest efficiency. We also have an architecture that can easily expand and grow to meet the changing demands of buildings. We're higher safety in application. We distribute that energy across a large surface area. We also maximize the solar hosting capacity of the electricity grid by minimizing that AC interconnect. And most importantly, we deliver the lowest cost of ownership. Again, my name is Andrew Tanner. I really appreciate your patience today. If you want to reach out to me, please do so over here or over here, Andrew@yottaenergy.com. Thank you so much.
Thank you, Andrew. Good job. Great. Well, that's it. You've heard 15 lightning talks. Amazing. It's now time for the audience to vote. And I'll just remind you the categories and then say, we're going to just tally these votes offline and we'll announce them on the platform afterwards, like who won for the best presentation and the highest potential impact. So that's what you're casting your vote for, to determine who is the first National Energy Storage Summit Pitchfest competition winners in those two categories. Of course, everyone's a winner, particularly amongst these finalists. What a fantastic feast of ideas. And I have great confidence now that we will get these solutions we need to scale energy storage to decarbonize the US in time. Here's the link on screen. Please go to that to vote, Pitchfest vote. You got 5 minutes, we'll keep it open. So we're going to try to keep the energy rolling and then pronounce on the platform. Of course, want to congratulate all of these finalists, not just those that get these votes. Tremendous job, each and every one of you, and also the other people that applied for this fest and weren't able to participate, but we're going to post their videos if they've sent them to us online as well afterwards. To the audience, thank you. Wonderful to have you. I wish there was a drum roll as you do your voting, but this will conclude the Pitchfest competition. Thanks to Meg and Noel and the team that organized this, and especially everyone, the entrepreneurs who participated and the lab scientists and folk that may not normally do this. Some of us do this as a business, competing for support from VCs and the like, but it's a big ask to get out there and put your idea on the table and present in such professional and clipped and short form. Really great effort. Thank you. Next up on the National Energy Storage Summit agenda, we'll start at 11:35, I guess. A little bit behind is the collaboration cycle session. So this is the bit focused on new connections to accelerate solutions. This is where you can get excited. That time has finally come. If you've been setting up one-to-one meetings, now's your hour. We have also set up 7 different themed collaboration rooms, multiple roundtable discussions that are a fantastic opportunity to dive deep into some of these industry needs we've surfaced, talking about how researchers can help, the hundreds of industry folk that have come online for this summit, new science and technology that can change the industry landscape in years to come will be discussed around these roundtables, and much more. The topics of battery recycling, AI and ML, the artificial intelligence, machine learning stuff we've been listening to in the Pitchfest. Really important conversation about Lithium Valley here in California, hydrogen, subsurface storage, and much more. And I just want to remind folk what I mentioned at the start of the day. Attendees at this next session will have the amazing opportunity to apply for a special collaboration seed fund, $20,000, thanks to the University of California, so that if you've got great ideas and you've been inspired by this Pitchfest, you can accelerate those ideas and form new partnerships from the cycles that you're about to go through, the collaboration cycle session, and apply to get funded to build something new. I reckon we're going to have a lot more than $20,000 worth of value created in the next hour. Head back to the program icon on the left of the navigation bar to choose your roundtable. See you out there. Thanks so much for tuning into the Pitchfest, and thanks again to the pitchers. That was fantastic.